Okay, let me begin by just reviewing techniques for multivariate data. Linear regression and correlation. Correlation is interested in measuring the strength of the relationship between two variables. Linear regression is trying to fit a straight line to the set of variables. Pearson's correlation coefficient. It's the ratio SXY over square root SXX SYY. SXY is the sum of deviations from the mean, product of deviations from the mean for both the x and the y values. SXX is just the sum of squared deviations from the mean for the x values. SYY, sum of squares of deviations for the y values. Fitting a straight line. The slope of the least squares line. This is the line that best fits the data. The slope is computed by dividing SXY by SXX. The intercept is obtained by subtracting from y bar b times x bar, b being the slope. Here's some scattergram patterns. And the values of R that correspond to those patterns. In the first pattern, there's no relationship between x and y. You can't predict the values of x from the values of y from the values of x. They're following the data, the scattergram is in a circular pattern. That circular pattern could convert to an ellipse where there's now some relationship between x and y. If the ellipse is sloping upwards, there's a positive relationship. Increase in the value of x generally result in the increases of y. The strength of that relationship can increase until it lies perfectly along a straight line. If you have the equation of that line, you can calculate the value of y exactly from the value of x. But you can have negative relationships where the ellipse is going downwards. Increases in x result in decreases in y. And the strength of that relationship can go up to where it's lying perfectly along a straight line. Then you can have non-linear patterns. I should point out that for nonlinear patterns, the value of R could be 0. So the value of R can be 0 if there is no relationship between x and y, but it also can be 0 for nonlinear patterns. The coefficient of determination, that's obtained by just multiplying R by itself, forming R squared. And that's really the proportion of variance in y that's explained by x. You can break up the variation in y, summarized by the sum of y minus y bar squared, into two parts. This is where I replace y by what's predicted from x. And this is the error in the prediction. This is sometimes called the sum of squares that's explained by x. This is the sum of squares that's unexplained. If the data lies perfectly along a straight line, this second one will be 0, and this one will be equal to the total variation. Sum of squares explained over sum of squares total is the coefficient of determination, and that can be easily computed by just squaring the value of R. We'll now look at techniques for analyzing categorical data. In categorical data, we're measuring categories. The measurements are categories, identifying categories of a variable. The bar graph, the frequency table. We go through to compute the frequency table, we just go through the data and count how many cases are in each category. To plot a bar graph, we draw above each category a bar whose height is equal to Fi. Usually the bars are not touching together to illustrate the distinctness between the categories. This example was data collected on across Canada on 34,000 subjects, 35,188. The variables were measured were mostly categorical, whether they used antidepressants, didn't use antidepressants, whether they used mood medication, anxiety medication. There's about 5 different medications. And so there was just 2 categories. The person had used it in the last 6 months, the person had not used it. In addition, they collected variables on gender, their income, their education, and another one was called role. Role was a combination of whether the person was a parent, working, had a partner. So there was actually, it was a combination of 3 variables, whether you're a parent or not a parent, whether you were working or not working, whether you had a partner or not working, or not did not have a partner. So these are the different categories of role. There's the frequency table for age. Actually, each age was represented approximately equal in this study. That was done on purpose. There's a bar graph of age. Here's the categories of age. This is the height of those bars equal to the frequencies of the different age groups. There's role. A frequency table for role. These are the number of cases of the 34,000 cases that fell into each of these 8 categories. There's a bar graph of role. The ones where the bar is highest is the ones that were most frequent. The ones that were lowest were where the categories of role that were least frequent. The least frequent one was when a person was a parent, had a child, but didn't have a partner and wasn't working. An alternative to the bar chart is a pie chart. You basically draw a circle, a pie, and then divide the circle into segments with the area of each segment proportional to the frequency. This is an example of a study that was done it was on head injuries. There was 22,540 people in Saskatchewan who'd had head injuries. The variables that were measured were what caused the head injury. These are the categories of that variable: motor vehicle accident, fall, violence, other vehicle accidents such as snowmobile, an industrial accident, and then other. Here's a graphical display of the categorical data. You can display it with a frequency table. You can display it with a bar graph. You can display it with a pie chart. There's the frequencies of the different mechanisms of getting the head injury. Most frequent one was motor vehicle accidents. There's a bar graph of the occurrence of the mechanism that caused the injury. There's the pie chart. The most frequent occurrence cause of the head injury was a motor vehicle accident. Handling multivariate categorical data. If you have two variables, the data can be displayed in what's called a two-way frequency table. From that, you can compute what's called the chi-squared statistic. The chi-squared statistic is interested in whether the two variables are related or whether they're independent of each other. So the chi-squared statistic is a technique for examining the dependence amongst two categorical variables. So the situation, we have two categorical variables, R and C. The number of categories of capital R is R, number of categories of C is C. We then observed N subjects and then count the number of subjects where R is equal to its ith category and C is equal to its jth category. This is displayed in a two-way table. Usually R are the rows, C is the columns. An example, here we're measuring blood pressure and cholesterol, and it was measured on 1,237 subjects. The measurements were done categorically. Now it's also done, it could have been done continuously. We'll do it categorically. These are the categories of blood pressure. These are the categories of cholesterol. So we set up a two-way table, blood pressure being the rows, cholesterol being the columns. No, blood pressure being the columns, cholesterol being the rows. And then we go through the 1,237 subjects and count how many subjects were in each combination of cholesterol, blood pressure. The last row is the total of the columns. The last column is the total of the rows. If I add up those, either way, we'll get the total number of cases, 1,237. Another one. This was coming from the drug use data. C is age. So that's the columns. The rows are going to be antidepressant use, whether they used antidepressants or not. A total of almost 34,000 subjects. This was done on a cross Canada survey. There's the two-way frequency table. Now, when the rows are just two categories, we can probably just compute the percentage that are where there's a yes. So this is the percentage antidepressant use. So you can see that it's going up, and it's highest with the age group 50 to 59, and then it goes down. There's a bar graph of the percentage of antidepressant use going against age. If the two variables were independent, age group and antidepressant use, this would be a flat horizontal graph. The chi-squared statistic, this is a statistic that's used to measure dependence amongst two categorical variables. We'll let Ri be the total for the ith row, Cj the total for the jth column. Eij is Ri times Cj over n. This is the expected frequency in the ij cell if you had independence. So there's the table. The capital Ri's are the row totals. Capital CJ's are the column totals. The expected frequencies. These would be computed from the row and column totals. the formula is Ri times Cj over N. So for instance, E23 would be R2 times C3 over N. The justification for this formula. Eij is Ri times Cj over N. So I can bring the Ri down to here. So that's basically saying the proportion in the ith row that's in column J, that would be E23 over R2. That's the second row proportion in the jth column. That's the same as the proportion in the overall. You can bring the Cj down to there. That would be saying that the proportion in the jth column that's in row I is the same as the overall proportion in the same row. And that would be true for every row, for every column. So the distribution amongst the rows is the same for each column. The chi-squared statistic, you'd sum over all cells, I going from 1 to R, J going from 1 to C, Xij minus Eij squared over Eij. If Xij is the observed frequency, Eij is the expected frequency if you assumed independence. So if independence was true, these would all be small and chi-squared would be small. Let's apply this to the blood pressure cholesterol example. Total of 1237 subjects. There's the table. Is cholesterol related to blood pressure in any way? Or is cholesterol independent of blood pressure? First step is to compute the expected frequencies in each of the cells if there was independence. There's the expected frequencies. This number here is the row total times the column total divided by n. When this is true, the distribution across columns is the same for each row. The percentage in each column is the same for each row. And this is the same as the overall percentage in each column. The same is true for the way the subjects are distributed amongst the row categories for each column. That's the same for each column. And it's the same as the overall. There's another version of that table. On the top, we have the expected frequencies. In the brackets in the middle, we have the observed frequencies. And in the bottom, we have what's called the standardized residuals. These are just measuring how close the observed frequency is to the expected frequency. That's how that's computed. That's how the 2.11 is computed. If I sum and square those observed residuals, I get the chi-squared statistic. So this is how the standardized residuals are calculated. Observed minus what you'd expect under independence of the square root of what you'd expect. And then the chi-squared statistic is just obtained by squaring each one of these terms and adding them up. Example, this comes from the drug use one. One of the variables is rho, the other one is antidepressant use. There is the two-way frequency table. This is just another way of representing it. This is giving you the percentage of antidepressant use amongst the people who had different roles. It looks like if you were a parent, you were working, but didn't have a partner, that's the highest use. You were a parent only, didn't have a partner, didn't have a child, that's the second highest use. Look at the graph of percentage of antidepressant use versus the different roles. There's how we calculate chi-squared. There's the observed frequencies. There are the expected frequencies assuming independence. That would be the row total times the column total divided by n. There's how you'd compute the standardized residuals. Observed minus expected over the square root of the expected. There are the residuals. So the calculation of chi-squared is just summing and squaring the residuals. You expect, if there is independence, you expect all of the residuals to be small. Roughly, they'll lie between -2 and +2. The values outside of that range, where the observed residuals are out, indicate cells where there's great departure from independence. If it's positive, it means the observed frequency was much higher than what you'd expect in the case of independence. Here's another example. This was the subjects in this example were individuals who'd been victimized twice by crimes. The rows are the crime of the first victimization, columns are the crimes of the second victimization. There are the columns. This is rape, assault, robbery. This is pickpocketing, personal alarm. This is motor vehicle theft. Now, is there a relationship between the first victimization and the second victimization? If there is no relationship, then the expected frequency would be row total times the column total divided by n. There are the standardized residuals, which would be observed minus expected under independence divided by square root of it. Those should be all close to 0 if there is no relationship between the crime and the first victimization. But notice that all of the ones along the diagonal are very large values, meaning that the occurrence there was much larger than if it was different. So this shows you that if you are victimized by a crime at the first victimization, it's likely that the second victimization would be the same crime. The chi-squared is the measuring in the whole table how close the observed frequencies were to the expected frequencies when you assume independence. The next topic, probability. Probability are mathematical. Probability is our mathematical models for random phenomena. You can break up phenomena into two groups, deterministic and non-deterministic. Deterministic phenomena are ones where you have a model that you can predict the outcome exactly. A lot of these occur in physics. If you know a rocket ship is going up at a certain rate, or a ball is thrown up at a certain rate, you can predict exactly where it's going to land pretty well. Non-deterministic are phenomena that can't be predicted. So in deterministic, there's a perfect mathematical model that allows you to predict the outcome of the phenomena from data collected from the phenomena. Many examples are in physics and chemistry. Non-deterministic, you don't have a mathematical model that can predict the phenomena's outcome. You can break up non-deterministic into two groups, random and haphazard. Both of these you're unable to predict the outcomes. But in random phenomena, in the long run, if you observe it for a large number of times, the outcomes have some sort of statistical regularity. Haphazard are for phenomena that are unpredictable, and there's no long run exhibition of statistical regularity. So you can break up non-deterministic into two groups, haphazard and random. In random, if you perform them a large number of times, there's some things that can be predicted in their occurrence. Haphazard, no long run exhibition of statistical regularity, unpredictable outcomes. I'm not sure that these exist, because if you observe something for a large number of times, quite often a pattern exists. Some examples of random phenomena. Tossing a coin. There's two possible outcomes, a head or a tail. You can't predict on each toss whether it's a head or tail, but you can, in the long run, if you do it a large number of times, 55% of the times it comes up heads, 50% of the times it comes up tails. Rolling a die. The outcome is the face that's facing upwards after the die is rolled. You can't predict whether there's 6 possible outcomes. You can't predict on a single roll which one it'll be, but you can say each one of those is equally likely. If you performed it a large number of times, each one of those should occur approximately the same proportion of times, which was 1/6. If the die was not balanced, then it could occur that one of those outcomes occurs at a higher percentage of the time. Some definitions. The sample space for a random phenomenon. It's the set of all possible outcomes. So if I go back here, rolling a die, the sample space is the different possible outcomes. If I'm tossing a coin, there's just 2 outcomes possible, head and tail. So tossing, there's the sample space for tossing a coin. Just has 2 possible outcomes. For rolling a die, 6 possible outcomes. An event. An event is a subset of the sample space. It's a set of outcomes. Of a random phenomena. You can illustrate an event with what's called a Venn diagram. The rectangle represents all possible outcomes. The event is the subset of outcomes. You say the event has occurred if the outcome lies in E. Example, rolling a die. There's the sample space, set of all possible outcomes. An event is just a set of those outcomes. One event is you roll an even number. That would be 2, 4, and 6. These are the outcomes that represent that event. The null event. This is a special one. This is the one that contains no outcomes. The entire event. It's the event that includes all of the outcomes. The empty event never occurs because one of the outcomes has to occur. The entire event always occurs. Methods of combining events. First method is union. It'll be noted. So you have two events, A and B. These are two subsets of sample space. The union is the set of all outcomes which belong to A or to B or to both. So it's that shaded region. The union occurs if A occurs or B occurs. So if the outcome is either in the set A or in the B, then A union B occurs. The intersection. Let A and B be two events. So they're both sets of outcomes. The intersection is the set of all outcomes that belong both to A and to B at the same time. That's illustrated by this diagram. That's the intersection. A intersection B occurs if A occurs and the event B occurs at the same time. So usually you're working with union if there's an or between the two events. You're working with intersection if there's an and between the two events. The complement. Let A be any event. The complement of that event, I'll denote it with an A with a bar across. It's all of the outcomes that don't belong to A. So there's the shaded region is the event A complement. The event A complement occurs if A does not occur. So you recognize you're working with the complement if you see the word not. So union if you see the word or, intersection if you see the word and, complement if you see the word not. Mutually exclusive events. These are ones that are separated. They have no outcomes in common. A intersection B is equal to the empty set. When two events are mutually exclusive, they can't occur at the same time. A can occur, but that means that B doesn't occur. B can occur, but that means that A doesn't occur. If you have two events that are mutually exclusive, they have no outcomes in common, they can't occur at the same time. The outcome of a random experiment cannot belong to both A and to B if they're mutually exclusive. Probability. Here's a definition of probability. This is a specific definition. Suppose the sample space, it's the set of all possible outcomes. Suppose it contains n such outcomes, and suppose also they're equally likely. Then the probability of the event E is the number of outcomes in E over the total number of outcomes, the number of outcomes in S. The symbol n brackets A is counting is just denoting the number of elements that are in A. This is a special case of the definition of probability. It occurs when there's a finite number of outcomes in total, and each of those are equally likely. This occurs quite often. Some rules for probability. The probability of A union B is P of A plus P of B. This is if A and B, A intersection B is the emptiest set, A and B are mutually exclusive. That's the additive rule of probability. Probability of A or B is equal to P of A plus P of B. But this is only true if A and B are mutually exclusive. If you count the number of outcomes in A and the number of outcomes in B, number of outcomes in A union B will be number of outcomes in A plus the number of outcomes in B. Divide by the total number of outcomes, it converts it to probability. So if the two events are mutually separated, P of A union B, that would be A union B is the shaded region. That's equal to P of A plus P of B. The additive rule in general, P of A union B is equal to P of A plus P of B minus P of A intersection B. So this is true in general, in particular when the two events are not mutually exclusive. When the two events are not mutually exclusive, you add up P of A, P of B, then the outcomes in A intersection B are counted twice, and you have to remove that. So when P of A and P of B is added together, A intersection B is counted twice, so you have to remove that so that they're only counted once. Example. Suppose that Saskatoon and Moncton are applying for the World University Games. The organizers have narrowed it down to 5 cities. Suppose there's a 20% chance that Saskatoon will be amongst the 5. A 35% chance that Moncton will be amongst the final 5. And an 8% chance that both will be amongst the final 5. What's the probability that Saskatoon or Moncton will be amongst the final 5? That's or means union. So let A be the event that Saskatoon is amongst the final 5, B be the event that Moncton is amongst the final 5. I'm just going through the problem and putting down P of A is 0.20, P of B is 0.35, P of A intersection B is 0.08. Probability of A union B. A union means or is equal to P of A plus P of B minus P of A intersection B. 0.20 plus 0.35 minus 0.028. This is because in this sum here, A intersection B has been counted twice, so I have to correct for that. Rule for complements. P of A complement is 1 minus P of A. So the probability of A not happening is 1 minus P of A. A is any event. The complement is everything outside of A. A complement occurs if A does not occur. A complement and A are mutually exclusive. Can't have A occurring and A not occurring at the same time. The union of A and A complement makes up the entire sample space. The probability of the entire sample space is 1. That's equal to P of A plus P of A complement using the additive rule. So bringing the P of A over to the other side, P of A complement is 1 minus P of A. Conditional probability. Frequently, before observing the outcome, you're given information. Somebody's told you some information about the outcome. How should this information be used in predicting the outcome? Namely, how should the probabilities be adjusted to take into account this information? Usually, it's given in the following form. You're told that the outcome belongs to a certain event. Suppose we're interested in computing the probability of A when we're told that B has occurred. The conditional probability of A given B is denoted by this symbol, A given B. That's equal to P of A intersection B over P of B. This can only be calculated if P of B is not equal to 0. If P of B is equal to 0, you wouldn't have been told that B has occurred. This is the rationale behind that formula. Here's the event A. Here's the event B. Now, if you've told that the event B has occurred, then the sample space becomes the set of B. The probabilities won't add up to 1 unless we divide them all by P of B. A then can occur only if the outcome is in A intersection B. So the probability of A given B is the probability of A intersection B over P of B. The reason you divide by P of B, you want to assure the probabilities add up to 1 in the new sample space. Example. Suppose the Academy Awards is going to be shown. Suppose you have a married couple and the probability a husband is going to watch it is 80%. Probability his wife is going to watch it is 65%. The probability that both will watch it is 60%. If you're told that the husband is watching the show, what's the probability his wife is also watching the show? So to do this type of problem, you define events. B is the event that the husband is watching the show. You're told that P of B is equal to 80%. A is the event that his wife is watching the show. You're told that P of A is equal to 65%. You also chose that the probability both are watching the show, but both A and B are occurring is 60%. So if you're told that B has occurred, probability of A is P of A intersection B over P of B. P of A intersection B is 0.60. P of B is 0.80. That works out to be 75%. So if you don't know that B has occurred, the chance the wife is watching the show is 65%. If you're told that the husband is watching the show, that 65% goes up to 75%. So maybe we'll just stop at this point.
Professor, I have a question.
Sure.
I checked my grade for the computer assignment 1, and I was surprised to receive a grade of 4 out of 10. As yesterday, would you be able to change that, or what's?
Sure, I would. Of course, I would. So some people submitted the probably by, other than a Word document. You might have submitted the graph by some other means. The graph didn't show up, so I can change that.
Okay, yeah, I submitted it as a Word document. I had my graph attached and a couple sentences explaining the relationship.
Yeah.
But yeah, I can try to resubmit it if that's necessary.
Sure. Like if you can paste the graphs into the Word document, then I'd see the I'd see the graphs.
Yeah, okay, that's what I did.
Okay.
Would
For
you like
some
me to
reason,
just send you an email then so you can change it?
yes,
You know who I
sure.
am?
Yeah. Send me
Okay,
an
I'll send one
email,
right now. Thanks.
and on the email say you got 4 out of 10, and I'll change that to 10 out of 10.
Okay, thank you very much.
Okay,
I have a question.
sure.
Um, is the assignment still like due at midnight today,
Yes.
or was it due earlier? Okay, so I still have time
No.
to finish it.
Yeah.
Okay.
And actually, I will mark all assignments that are submitted late. Okay.
I
Okay.
have a question for you. Is it how do I I'm not sure how do I submit my assignment.
Uh, okay. Well, I would do a graph. Okay. And you can take a screenshot of the graph. Okay. And paste that into a Word document. And then below the graph, then in the Word document, just put some interpretations of what the graph means.
Okay, and why should I submit the assignment? Is it by the Canvas?
Yes, go into Canvas. I'm not sure how it's done, but a lot of people have done it. Yeah, I think
Oh,
you can submit a Word document as your solution to the assignment.
thank you.
Sure, I think that works as well with other courses. If you have to write if the assignment is writing an essay in English, okay, I think you write it in the Word document and then you submit the um, essay in Canvas.
I got another question.
Sure.
So I just kind of forgot, but last lecture I asked about how to access the Excel file because it just wasn't showing up. So I couldn't find the thing on the bottom right corner that you were clicking on.
The
Who?
VPN.
Yeah, the VPN. Who did you contact for
Well,
help?
I actually wasn't able to find that at the beginning. What you do is you contact IT services, and they
IT?
will, yeah. If you go
Okay.
search in on the university thing for IT, there's a contact thing there. You can either email them or possibly phone them. Okay, and then they will help you with that.
Okay, thank you.
Sure. So we'll stop at this point.